This video is all about the discriminant. The discriminant is the stuff inside of the square root of the quadratic formula. The stuff is, as you recall, b squared minus 4 times a times c. We're going to use the discriminant to help us figure out how many x-intercepts, otherwise known as roots, that there are. So just recall roots, zeros, solutions, x-intercepts are all kind of talking about the same thing. You use them interchangeably. I'm just going to walk through a couple examples, and through these examples we'll see all the work that's unnecessary to do to figure out what's going on in the graph. If I'm just simply asked how many roots there are, we don't want to go through this whole process of graphing, and we can simply use the discriminant to help us figure that out way faster. So let me just go through this first example here. So we got an equation y equals negative x squared minus 2x plus 24. Now there's a couple things I can intuitively figure out without doing all this process you see here. What I can do is see that, all right, this number that's in front of my leading coefficient, the number in front of the x squared, is negative. That tells me that my graph is going to be concave down. And that's always the case if you consider in general that any quadratic is ax squared plus bx plus c. If the a value is less than 0, meaning it's the a is like a negative number, that means that my graph is going to be this concave down. That's just a fancy way of saying it opens downward like this. It goes down. So I can see that it's going to be concave down. The other thing I can see very easily with this standard form is this 24 tells me the y-intercept. Because look, if I let x equals 0, that's how I find the y-intercept, right? If I let it equal 0, this term is going to go to 0, this term is going to go to 0, and I'm left with the 24. So there it is. So we can very easily see the y-intercept is 24. So with that in mind, that kind of tells me, well, I know this point right now. I know this point 0, 24 exists. And I also know I'm concave down. So for me to have a point above the x-axis like this, it tells me that my graph needs to be some variation of passing through and going down like this. I know that there's going to be x-intercepts. So it can kind of do this in this indirect way. But that takes some experience and just understanding these ideas. So let's just imagine we didn't notice that and we didn't use a discriminant. We didn't do the easy route to see how many roots are going to be. Let's just say we want, okay, you know what? I just want to graph this thing. The easiest way I recommend to go about graphing a quadratic is to try and factor the quadratic expression first. In this first example, we can. Before I start factoring, I like to not have a negative in front of my x squared term. So what I did first was factor that negative out, and look what just happened. These signs just switched around. They just became the opposite when I do that. So then I looked at what would add up to be 2 and multiply to be negative 24, and I got these values 6 and negative 4. Because this was an expression with a 1 in front of the x squared term, I could simply just look at this. This is my framework. I can just put in my 6 and put in my negative 4 like that. All right. So to find the x-intercepts from here, it's very easy. We have this in factored form already. So when I let y equal 0, I have this. And we know that there's two ways that we can get 0 as a result here. One way is to make sure that this bracket is 0. Because if this bracket's 0, it doesn't matter what this other bracket is. It's 0 times whatever gives you 0. So that's our one case. And here's the case I did right here. X plus 6 equals 0. The other way we can get 0 is if this bracket is equal to 0. because 0 times whatever gives you 0 once again. So we have x minus 4 equals 0. This tells me my x-intercepts, because my solutions are x equals -6 and x equals 4, my x-intercepts are -6, 0, and 4, 0. So let me go ahead and write those in. -6, 0, and 4, 0. Okay, so we've got our x-intercepts and we have a y-intercept. Another key characteristic we want to find out is the vertex. So I'm going to take the average of these two x-intercepts that I found. So what I do, how I find the average is we go x, this first x value plus the other x value, and divide it by 2. Because what's that going to do is it's going to take me, so here's my one x value, here's my other x value. When I take the average of them, it's going to take me to the value that's perfectly in between them. And that's what we need because of symmetry. We need quadratic equations. We know there's symmetry. So we need every point that's at the same height. You can see here the x-intercepts are at the same height. They need to be the same distance away from this axis of symmetry. And in this case, it's 1, 2, 3, 4, 5, 6 away. 6 away, 6 away. Okay, so we now know that x value of my vertex is going to be somewhere along this green line I just drew. So let's put this x value of my vertex into my original equation. So I could put into this equation or this equation because they're equivalent to each other. Doesn't matter. So I put the -1 into, I decide in this case to put it into here. And I get, when I do that, negative, so I'm looking at this now, negative of -1 plus 6, -1 minus 4. That turns out to be y of the vertex is going to be 25. So my vertex is -1, 25. So let's put that into our graph. Notice in my y-axis I decided to count by 3s just so it fit more nicely. So keep that in mind. I count by 1s on the x-axis. So we have so 25 is around here, right? Because we're going to have 25, 26, 27, right? And this is decent to be able to draw this. But let me just point out one more thing. We can look at the pattern. So I did the pattern down here. Because my a value is -1, I know typical, if my y equals x squared, for example, the pattern would be 1 over 1 up, 1 over 3 up, 1 over 5 up, 1 over 7 up, as we learned before. But this is a -1. This is a situation where we've got like a negative x squared term. So that makes my pattern going downward instead. So from my vertex, I'm going to go, look, it actually works out perfectly with my y-intercept. 1 over 1 down, nice. 1 over, next I go 3 down. So here I am. Then I go 1 over 5 down. So 3, 4, 5, 5 down. 1 over 7 down, 1, and then another 6 over here. And then perfect. We wanted to go 9 to get back to the x-axis, so this worked out perfectly. Everything fit nicely, and that should happen. If it doesn't happen, some kind of mistake happened. The pattern, the intercepts, the vertexes, they should all fit together. So right now I'm just going to use symmetry to get the other side. So look, I'm right here, so I'm going to put the other one at the same height there. This one, boom. So symmetry makes it a lot faster to kind of finish up the picture. So here is my finished graph. Hopefully I get this not bad. And well, so here's my graph of this quadratic. As you can see here, I have 2 real roots in this expression. And this is what we primarily try to figure out here. Yeah, we got the graph. That was a lot of work, took a lot of time. All I really wanted to figure out is how many roots there were, meaning how many x-intercepts there were. So in conclusion to this question, I should write, we have to write it up here because I don't have space. I'm going to say there are 2 distinct. Distinct means you can tell things apart, which means let me just move over here. Two distinct real roots is my final answer. Distinct tells me that the x-intercepts are different. They are in different locations. You can tell them apart. So there's two distinct, they're real. You can see them. They exist in the real space, and obviously roots, that they're the x-intercepts. So here is your answer. So let's box this answer. Done. So that is the answer to our first question. All right, let's move on to example 2. You can see here that this quadratic is a perfect square trinomial, which means that we use this pattern right here, as you recall. So I noticed there's a perfect square trinomial because when I looked at it, I noticed, oh look, I can square root this first term. I can also square root this last term. When I do that, I end up getting 2x and 3. Now I need to do a little check to make sure that the middle term follows this pattern right here, right? The 2 times a times b. And it turns out that we end up getting the 12x that we wanted here. All right, so we've noticed this perfect square trinomial. That allows me to then express this trinomial as this binomial squared. So we just take this value, put it here, and noticing that the middle term is negative means we put a negative here in the middle, and then we take our 3 and put it here. All right, so here is our factored form. You could think of 2x minus 3 all squared as 2x minus 3 times 2x minus 3. And put this on pause for a second. I just want to show you that we could actually express this in vertex form. And vertex form is nice, right? Remember, vertex form looks like this. It's ax minus h squared plus k, right? That's our vertex form. Notice that we don't want a number in front of the x here. So what we have right now is a 2 in front of the x, so it's not quite perfectly in vertex form. So let me kind of show you a little trick or a method here to try and make it look like vertex form. So I'm going to play around with factoring inside the bracket first. So let's just keep our squared intact like this. I'm going to just kind of make a couple adjustments to what's inside the bracket. I'm going to factor this 2 so that I get this x. That'll be nice because I get 1x. And to do that, I need to divide the second term by 2. So look, if I distributed this back out again, we'd have 2 times x, which gives me the 2x back. And then look, once I distribute this 2 into here, 2 times negative 3 over 2 gives me 3 back. Right, so we are good. That worked. So we haven't changed anything. It's still equivalent. We just kind of made it look a little differently. Now I'm going to use my exponent laws. We know that when things are separated by multiplication, we can just apply this squared to each thing. So we now have 2 squared, and then we need to now go x minus 3 over 2 squared. As you can see, we now get, so 2 squared is 4, and then we have our x minus 3 over 2 squared. This right here is vertex form. So this tells me that my vertex is, because it's x minus 3 over 2 in the bracket, we say it's 3 over 2 is our x value. And because there is no value here, it's just like plus 0, that means that my y value of my vertex turns out to be 0. All right, so we have a vertex that way. We can think of 3 over 2 as the decimal form, which is 1.5. That's useful when graphing, right? So we know our vertex. We need to find our x-intercepts, and I did that already. So I got right here, I let y equals 0, and I'm going to use my factored form for this. So I've got my 2x minus 3 times 2x minus 3 equals 0. As before, we just take this bracket, we let that equal 0, and we get x equals 3 over 2. And likewise with this one, same idea. We end up getting x equals 3 over 2. Notice that our x-intercepts are the same values here. So they're both of my x-intercepts are at the same place, which is at 1.5. So let's draw that in. So we got 1 and the other one's here as well. Now that we have our x-intercept and our vertex, you could actually notice something a little strange. Our x-intercept and our vertex is at the same place. And that is the only way that we can get an x-intercept that's at the same location. It must be the location of our vertex. All right, let's draw our vertex in here. So the vertex is 3 over 2, 0. Because things are not spread out like the previous example to draw the graph, we're going to need to use the pattern. So we notice that in our vertex form that we have right here, that we have a 4 out front. And it's the same 4 that you see out front here. So because our a value is 4, we're able to use our patterns. We got usually it's 1 over 1 up, 1 over 3 up, 1 over 5 up, but now we just multiply that by 4. So we have 1 over 4 up, 1 over 12 up, and 1 over 20 up. So that's a pattern I'm going to use. 4, 12, and 20. I decided to count by 4s in the graph so that fit nicely. Our first 1 over 4 up is going to take us here. And then if I go then 1 over, what was it? 12 and 20. So we go 1 over now 12 up. So 4, 8, 12. We're at 16 now. And then we're going to go 20 up. So from here, 1 over 16 is going to take us up to 36. And using symmetry, we're going to draw it going the other direction. And here is our graph. Now this question, once again, was concerned with how many roots we have. How many x-intercepts do we have? You can see here that we only have 1. But we don't just say 1 root, because as you see here, we've got 2 x-intercepts. They just happen to be the same thing. So what we say is 2 equal, they're real, and they're roots. 2 equal real roots. That is our final answer. After all that work, that's it. We don't want to do this. All right, so I guess a rule you can use is if you notice you have a perfect square trinomial like this, it means you're going to have 2 equal real roots. That's kind of the fastest kind of way to understand. But then later, once again, we're going to use discriminant to get this answer almost as fast. Discriminant's very powerful. Just quickly answer this type of question. So we don't have to go through all of this work. On to our final example. As you can see here, this is not a perfect square trinomial. You can't square root this, and you cannot square root this. All right, we can't use that. Can we factor? Let's try. So we need to add up to be -4 and multiply to be 5. This is not possible. We can't figure out any integer values that will accomplish this. So what I turn to next, I could use complete the square and find where the vertex is. So let's go ahead and do that. I used my technique, so I need to have a 1 in front of my x squared. So what I did is I factored out the first 2 terms. I factored a 2 in front. So I've got 2 times x squared minus 2x plus 5. Now I'm ready to do my 0 pair. Remember, for your 0 pair, what you do is you go, you take this value right here, beside the x value, and we divide that by 2, and then we square it. We get -1 squared, which gives us 1. So that's why I decide to use, for my 0 pair, I said 1 minus 1. This is going to create a perfect square trinomial for me, right? So this is the result. My perfect trinomial is right here. And as a result, we get x minus 1 squared. And just a little trick, let me just kind of show you something here. The way I got this binomial squared, I just take this value inside the bracket before I square it. And that just goes right here. And if you expand this out, you'll notice that this perfect square trinomial is here. We can actually expand this out, expand this guy out, and we'll get back this. All right, next thing I did was now move on, and I distributed my 2 through the bracket here. I went 2 times x minus 1, and then I went 2 times the negative 1. Then I got the negative 2 plus 5, and here is my nice vertex form that comes as a result. So I have my vertex at 1 because this is a negative 1 inside the bracket, so it becomes a 1 here, positive 1. And then here I got my 3, so that's my y value of my vertex. So we're good to carry on and draw that onto our graph. So we have 1, 3. Here it is. Let's label the vertex 1, 3. Now I kind of saved this moment to show you, and this is where it gets, and we really need you to pay attention here. This is the most important part, I'd say. So because we were not able to factor, it does not necessarily mean that there are no x-intercepts. It means that they're not nice integer values or nice fractions. There's still a chance there could be an x-intercept. So don't just say, oh, it's not possible factor, therefore there's no x-intercepts. There still could be. And let me kind of show you how we truly check to see if there are x-intercepts. What we need to do is let our equation equal 0. Because we cannot factor this quadratic right here, we can instead use a quadratic formula. So my a value is 2. My b value is negative 4. My c value is 5. I input that into the quadratic expression, the quadratic formula, sorry. So I've got b is negative 4, so I have negative of negative 4. I've got in here also, like I have to also put my b value in here. So I've got negative 4 squared. My a value is 2. Here and here becomes 2. And my c value is 5. Look here. We've got negative 4 squared gives me 16. And then I've got negative 4 times 2 times 5. 4 times 5 is 20 times 2. So we actually have minus 40 here. We have 16 minus 40. All right, that gives us a negative result, right? That gives me negative 24. This is a huge problem. You put this in your calculator, you're going to get error, error. You're going to get something that the calculator doesn't understand. And that's because it's actually this negative 24 causes this to be an imaginary number. It doesn't exist in the real space. So we're going to have x values in our solution that do not exist in the real space. We can't draw them on our graph. It's actually something called a complex number, which I won't get into here, but something you can look up. Look up complex numbers. So the fact that we have no x-intercepts, the fact that this is, we use the quadratic formula, that we get a negative inside the square root there, means that we have no real roots. And that is our final answer. All right. Now, if I wanted to just draw this for fun, let me just go ahead. I would look at my vertex form here, and I'd look at my a value and use my pattern instead. So my pattern tells me that I go 1 over, usually it's 1 up, 3 up, and 5 up, but because a is 2, I go 2 times 1 up, so it gives me 2 up. 2 times 3 up gives me 6 up. 2 times 5 gives me 10 up. So that's the pattern I'm going to use. So I'm going to go 1 over, 2 up, 1 over, 6 up, so 2, 4, 6 up, and then 1 over 10 up, 2, 4, 6, 8, 10, I'm up here, and use symmetry to get the remainder of the values. So now that I have my point using my pattern, I can draw the graph. So as you can see, this never touches the x-axis. And let's just put this somewhere nice. So we have no real roots. That's what we want to find. So once again, that was a lot of work for something that I'm going to show you right now. All of these questions we just did can be done speedy by using the discriminant. All right, finally, let me show you how to do this most efficiently by using the discriminant. What we're going to do is look at our 3 examples we just completed, but do this in a way more efficient manner by using the discriminant. What you're going to do, like we have been with the quadratic formula, is distinguish our a values, b's and c's. So we've got -1, we've got -1 here, we've got -2, and we've got 24. All right, just input these values into the discriminant. We've got -2 squared minus 4 times -1 times 24, and that gives us 4, and -4 times 24 is 96. So we've got negative, so it's plus 96. Our discriminant turns out to be 100. Because the discriminant is greater than 0, that is going to mean that we have the 2 distinct real roots. And why is this the case? Why does it mean that we get 2 distinct real roots when the discriminant is greater than 0? If you look at the quadratic formula, so I think I have it to start up here. Here it is. Let's just focus on this right now. If this value inside the square root is greater than 0, it means we're going to get 2 different answers depending on whether we use plus or minus. That's the important piece. We're going to get whatever this starting value is, then we're going to go plus some value, then we're going to go minus this same value. It's going to give you 2 different answers, always. So that's why we get 2 distinct real roots in this scenario. All right, so there's that one. Now let's look at our second example. In our second example, we saw that there were 2 equal real roots. We only had 1 x-intercept, if you recall. So let's once again use our discriminant. It's way faster to answer this type of problem. So we got 4, -12, and 9 for our a, b, c values. Put those into the discriminant. We've got, -12 squared minus 4 times our 4 times our 9. -12 squared is 144. 4 times 4 times 9 is also 144. And take a look, we get 0 here. Generally, when our discriminant is 0, this means that we have 2 equal real roots. It means we have kind of like 1 x-intercept. And take a look why this is. If my discriminant, let's look right here again. If my discriminant is 0, means all of this is 0. When I go plus 0, minus 0, it's not going to change the answer, right? I'm going to have negative b over 2a is going to be my answer because I'm plussing 0, minusing 0. Both of those results are going to yield the same value of whatever negative b over 2a is. So that is why we get 2 equal roots in that case. And then going back to our, oops, right, a little too far. Going back to our third example, this is the one where we just did, and we noticed, look, there are no real roots here. There's no x-intercepts. And so we get 2 here, negative 4 here, 5 here. Put that into discriminant. We get our negative 4 squared minus 4 times 2 times 5 means we get 16 minus 4 times 2 times 5 is going to give me negative 40, which is negative 24. My discriminant, whenever your discriminant is less than 0, so it's a negative answer, it means no real roots. There you have it. We've seen in a very painful way, but a very impactful way, how awesome the discriminant can be at answering these type of problems, where all we're trying to really find out is the nature of the roots. We want to know, are there 2 distinct real roots, 2 equal real roots, or no real roots? As you can see here, I did this problem for these 3 examples really quickly, not much space. If we don't do it this way and we go about graphing, look at how much work we have to do. So avoid that if possible. As always, good luck, and I hope this helped.